Okay, well, hello everyone. Welcome. Good morning. Welcome to college algebra. Let me see here if I can get myself situated. Okay, here is our PowerPoint presentation. All right, okay, welcome to college algebra. Remember, this is what I've got in mind here is a full year course where the first term, as always in math, we're always preparing for the next course. That seems to be the world of mathematics. We're always getting ready for the next course. The current course is not what's really important. It's the next course. So we kind of have a bit of that here because my idea was to teach a course in calculus. I've been asked over a number of years of teaching. Like I said, I've been with teaching in call. This is my 6th year. I've been asked over a few times, well, more than a few times by students, I've taken calculus way back in the day, and I never really quite understood what was going on. I could do some of the algorithms and do some of the problems, but I really never knew what the heck the whole thing was really all about. And so I thought I would, try to do that. People would be interested, or people interested just in general of what is calculus. They didn't have the chance to take the course. So that was the whole kind of motivation of doing a year of math. And it seemed to me that you just can't walk into calculus without having a real good foundation in basic algebra. You also need analytic geometry, of course, but I thought we could do that during the course. It's the algebra that was the problem, how much algebra I could assume that people know. So I want to thank you guys for making the responses. Almost everyone responded. It's great. I think 3 of you did not respond, and you know who you are. It's not too late to shoot me an email with your opinion about the algebra question. And what I found was there's 25 students registered. I don't know exactly how many students we have this morning who are with us, 21. But of the 22 respondents, about 9 of you said, my algebra is kind of like on the 9th grade level, more or less, pretty much, I think. So that's a good number. That's a good number of people. The rest of you feel that your math is much stronger than that the 9th grade algebra would not be a problem. And that's really the foundation that I was looking for. We won't really be able to test your opinion of your math comfort, algebra comfort, really until the next class, until the next presentation at least. Because this presentation here, the one here on numbers, we're going to use a little bit of algebra. And you'll get an idea of, oh yeah, that's easy stuff. I follow that kind of algebraic manipulation, or you won't. And then you'll kind of have a small idea whether your algebra comfort is as good or as bad as you thought it was. It's really the next presentation where we start. I go over the basics of solving equations, and that's where kind of the rubber will meet the road, and we'll see just how good your algebra is. And that is where I'm trying to find how fast we can move through that, how much we actually have to do that before we can move on. As you all know, it is absolutely foundational. You cannot move forward with this kind of mathematics without really being comfortable with solving equations, because we're doing it all the time. And it has to be done quickly. It has to be done automatically. We can't be agonizing over every single algebraic manipulation. We'll get nowhere. It's fine when you're learning how to do that, but if your goal is to try to understand some calculus, then we just can't, and we only have 8 classes, then we really can't work at that rate. So let's see, when we get to the next presentation and we start looking at equations in earnest, we'll get an idea of just how everyone is doing. And just to throw out here that if some people do think they could use an extra class where we just spend some time slowly going over some of those mechanics that they knew long ago in the operations of solving equations, be very, very happy for us to find a time where we can schedule that with just the folks who think that extra class would be very helpful in moving forward. But let's not worry about that until we get to the equation solving. All right, so without further ado, let's talk about numbers. Here are our numbers. You can see we have the whole numbers, and we have the fractions, and we have the negative numbers, and of course we have the irrational numbers. So let's go through those. I thought it might be a good way to start our class by looking at the various different numbers that we'll be working with, and I found a few opportunities to use some algebra along the way, just to see how we're doing on that. Okay, so the whole numbers, we can have kind of two designations. One is the more formal, what mathematicians call the natural numbers, and they start with 1, 1, 2, 3, etc. And then we'll call the whole numbers if you add 0, a very important addition to the number system done by the Indian mathematicians around 500 AD. It's interesting when you look at the number line like that, going off forever, we see right away, the first slide, we meet infinity. There are an infinite number of natural numbers. There are an infinite number of whole numbers. Is there one more whole number than natural numbers? It would look that way just when you look at the first 10 or 11, but in fact, it's not true. There are as many natural numbers as there are all whole numbers. They both have this infinity of numbers. And we'll see that, what I mean by that in the next slide or two. But right away, we are faced with the idea of infinity. There's an infinite number of these numbers. We have nothing in the physical world that really matches that with our intuition. Right away, we are into the world of the mind. And this is one of the great fascinations of mathematics. It takes us into a different world. It takes us into the so-called Platonic world of forms, of ideals, as you remember from your early philosophy class. Okay, so looking at the whole numbers, the natural numbers, they obey certain rules, which the other numbers, as we expand our system, behave. There's the commutative law. It doesn't matter what order you add and multiply numbers, you'll get the same result. That multiplication symbol of the dot, we will try never to use in algebra. Multiplication is indicated by just juxtaposition. AB is the meaning of A times B. If we're really desperate, we'll use brackets if we have to, but we will never go to the dot notation. It's just doesn't really work in the context of algebra. The next law is the associative law. This is a law that we virtually take for granted. We don't even think about it as a law, but it doesn't matter what grouping you go ahead and add or multiply numbers. Doesn't matter whether you add the two back numbers first and then to the first number, or add the two. It just doesn't make any difference. Like I say, this is almost like, watching paint dry. We hardly think of this as a law, but in fact, it is a very important one, and we use it all the time, whether we know it or not, in simplifying our expressions. And then there's the two identity laws. We have the property of 0, that A plus 0 will always give you back A, no matter what A is. And the multiplicative identity law, that A times 1 will always give you back A, no matter what A is. 1 times anything also will leave it alone. And then the last law, the most important law for us, actually, in studying of algebra, in a sense, which is the distributive law, that when you multiply something times an expression of additions, you have the ability that you can multiply through that bracket, right? As we see with the law. And this is the foundation for factoring. And as we may remember, factoring is a big deal. And we'll see why when we get to that as we look at equations. But these are our laws of numbers, and they also are true for all the numbers that we'll be dealing with. But we see them right away here with the whole numbers. I'd like to prove our first theorem. we can prove using these laws that 8 times 0 is 0. Notice that's not one of our fundamental properties of numbers. This is a result. This is something that we can prove. And the proof goes like this. And the first thing that you see is you see a whole string of equalities. You will see this a lot. This is the way mathematicians write. Okay, this is as opposed to what we were used to maybe in high school of writing things down one line under the other. Takes up a lot of real estate for one thing, and it's kind of just a waste of space and a waste of time. So it's very, very natural for me, and hopefully it'll become natural for you over time, to just look at the equalities as they move across. Every single expression here is equal to all the other ones if we are valid in moving along from one to the other. And certainly, I think you'll agree that 8 times 0 is 8 times 1 minus 1, because 1 minus 1 is, in fact, 0. We can use the distributive law and multiply the a through. And of course, 8 times 1, as we know, is a, and minus a times 1 is also minus a. And we know that a minus a is 0. So, in fact, the first expression, a times 0, is the same as the last expression, 0. Okay, let's have a little fun with numbers before we get down to the real serious stuff. The Pythagoreans are the ones who are kind of credited in the ancient Greeks of actually inventing mathematics as we understand it. Babylonians and Egyptians used it very much as a tool that we'll be very interested in. But to play with numbers, to look for patterns, to study mathematics just for its own sake, because it's fun, because it's interesting, is something that was not known. That we do not see this in the record of any civilization until we come to the ancient Greeks and Pythagoreans, who lived around 550 BC up to the time of Plato, where their group kind of ended. We don't see them anymore in history, but for 200 years, they were a very big factor in Greek science and Greek mathematics. And here's one of their contributions. They looked at numbers in many, many ways. And one of them was as figures, using stones. And you can see here these triangle figures and the square figures. And not surprisingly, they called these the triangular numbers, those numbers, 1, 3, 6, 10, 15, on and on, because you could set them up as a figure of a triangle. And T1 is 1, triangle number 1. Triangle number 2 is 3, but notice just from the stones, triangle number 2 is 1 plus 2. That's where we get 3. And triangle number 3, T sub 3, is, if you just look at the stones, 1 plus 2 plus 3. So you can see in general that the triangular numbers are the sum of the integers from 1 up to that number. Triangle number 5 is the sum of 1, 2, 3, 4, 5, and in general. But in looking at the pattern, notice that T sub 2 is 2 times 3 over 2. Check that out, it's 6 over 2, which is 3, yeah, that works. T sub 3 is 3 times 4 over 2, yeah, that works. And T sub 4 and T sub 5, in general, T sub 5 would be 5 times 6 over 2, which truly is 30 over 2, which is 15. We have a pattern here. T sub n seems to be n times n plus 1 over 2. And this is the kind of stuff that we see in Pythagorean mathematics. This is totally unprecedented in history. No one ever played with numbers like this before, okay? Looking for patterns. This is mathematics as we understand it. And the square numbers, well, that's pretty self-explanatory. The square numbers are simply the integers squared, put into the square pattern. There's a great story of Frederick Gauss as an elementary school student, probably around 3rd grade. The story goes that he was in math class. I guess, wasn't such thing as a math class in 3rd grade, but they were in class. And the teacher had to do some administrative busy work. And so he wanted to keep the students busy for a while where he could turn his attention to some other paperwork that he had to do. This is how the story goes. Gauss lived in the first half of the 19th century. And so he gave his students a job, a problem that he thought would take him some time, keep him busy for a while. And he told them to add up the numbers from 1 to 100 and put that on your slate. And when you have the answer with all that work, you can put the slate on my desk and then go back and sit down. And he figured that people would be pretty busy, the kids would be pretty busy for a while, adding up the first 100 integers. Well, in less than a minute, Gauss walked up with his slate and put it on the teacher's desk with the number of 5,050. Apparently, the teacher had given this problem to students in the past, in other years. He did know the answer, and he was amazed that this little kid wrote down the answer within a minute. How could he possibly know this? And the story goes, he asked Gauss after class, how did you do this? And Gauss said, I saw a horseshoe in the air. The horseshoe ran like a rainbow from 1 to 100. And I saw 1 paired with 100, and 2 paired with 99, and 3 paired with 98. And each of these sums was 101. And there were 50 of them. I had 50 pairs. I had 50 pairs of 101. And that was easy to multiply 50 by 101. Gauss is considered one of the greatest mathematicians of all time. And this is just one of those great stories, which apparently is true. Another story is he helped his father with his bookkeeping when he was 4. He corrected his father's arithmetic mistakes and checked his work when he was 4 years old. So if you've never heard of Frederick Gauss, well, then you can't say you know too much about the history of math, because he is considered one of the greatest mathematicians of all time. You can generalize this argument to our T sub n. Remember, T sub n is the sum of the first n numbers, and you could do exactly what Gauss did. You could create this horseshoe, this rainbow in the sky, where 1 hooks up with n and 2 hooks up with n minus 1, etc. And here, if we have at least an even number of numbers, so I'm assuming here the simple case, that n over 2, half of n would save the place of 50, and that common sum of n plus 1 serves the placeholder of 101, and the formula would hold that the sum of all those numbers is n over 2, the 50, times n plus 1. And so there is what, in fact, T sub n is. We saw it in the pattern, and here is the proof in general, that T sub n is n times n plus 1 over 2. So if you wanted to know what, for example, T sub 20 is, sum of the first 20 numbers, it's 20 times 21 over 2, which is 10 times 21, which is 210. So just before we leave these patterns, just one more kind of piece of fun with them. Did you ever notice that 4 is actually 1 plus 3? Is one triangular number and the bottom triangular number. Well, isn't that T sub 1 plus T sub 2? So S sub 2 is T sub 1 plus S sub 2. And sure enough, S sub 3, 9, is in fact 3 plus 6. Again, splitting up that square. And T sub 4 is, right, 10 plus, I'm sorry, 6 plus 10 is, sorry, is 16. Again, you see the pattern. S sub 4 is T sub 3 plus T sub 4. And S sub 5, 25, is again the sum of 2 triangular numbers, T sub 4 plus T sub 5. So again, we seem to have a pattern that n squared, that square, can be written as T sub n minus 1 times T sub n. Now remember what these numbers are. T sub n minus 1 is the sum of the first n minus 1 numbers. T sub n is the sum of the first n numbers. You add those two strings together, you'll get n squared, no matter what n is. Can we prove that? We can with a little bit of algebra now that we know our formula for T sub n. T sub n minus 1, if you look at the form, is n minus 1 times n over 2. Because T sub n, you start with n times n plus 1. Well, now we have T sub n minus 1, so we start with n minus 1 times the next number, which is n. And T sub n is n times n plus 1 over 2. Notice we have a couple of fractions with a common denominator of 2. Therefore, we can certainly add those with the common denominator. We can add n minus 1 times n plus n times n plus 1. They're both over 2, so the whole expression is over 2. We can use the distributive law. We can multiply n in the back times n minus 1. We can multiply in the second term n in the front through times n plus 1. And we get n squared minus n plus n squared minus n. I'm sorry, plus n. And you notice that the n's cancel out. And what we have here is 2n squared over 2, which in fact is n squared, which is what we had claimed. Again, a whole string of equalities. Take a look at that, guys. That is 2 lines in which every single term I'm claiming is equal to the next term. And therefore, I can say that Tn minus 1 plus T sub n is equal to the last term, n squared, which is what I had claimed. So here's a little piece of algebra, right? We added common denominators. We multiplied through using the distributive law. We added up some terms. We divided by 2. So if this does not look good to you, if this looks like, oh, what exactly is going on here? Okay, then your 9th grade math is not as good as you thought it was. Okay, this is not difficult algebra. So this is one of the reasons why I wanted to go through this, was to kind of test the waters to see if this is good. Many of you, of course, have not looked at algebra for years and years and years. So this may be the first piece of algebra you've seen in 30 or 40 years. Well, and it's not going to be familiar, but take heart. Okay, as we work through this stuff will come back. You have to practice. You have to play with it yourself. It's not going to come back to you by just watching me. So do not be discouraged if, in fact, this does seem a little, little difficult. What the heck are you doing here? If you do have that reaction, please take heart. We'll be looking at this more carefully, all these different techniques, starting in the next presentation. One more pattern, one more piece of fun from the Pythagoreans. Again, we have our square numbers, right? And you can see that they kind of be created, they're kind of built up from these L's. But look at what the L's are. The L's are the odd numbers. Certainly 1 is equal to 1 squared. But look at what 4 is, okay? 4 is 2 by 2. Isn't that 1 plus 3? And here's 3 by 3, here's 9. And 9 is 1 plus 3 plus 5. And here is the square 4 by 4, which is 16. And sure enough, 16 is 1 plus 3 plus 5 plus 9. And we see, again, a very interesting pattern that the sum of the first set of odd numbers is the first sum of first 5 odd numbers is 5 squared, etc. So the sum of the first n odd numbers equals n squared. We're not going to prove this. This would take us into another branch of mathematics. And this is a whole other subject, right? This is the beginning of number theory. Like I say, this is the beginning of mathematics as we understand it. And if you were to take a course in number theory, math majors take such a course, or to study this on your own. This is very much how number theory starts with these warm-ups of looking at Pythagorean figurative numbers. But this is not our agenda. This is not what we'll be doing. Okay, as beautiful and as fun as this stuff is, we have another goal. We have the goal of trying to learn to use mathematics as a language to study basically nature. You can use the language to study anything and everything, as the modern world has shown, but our focus is going to be looking upon the world, the physical world, where mathematics really began and where it got so much of its early impetus through the Renaissance and the scientific revolution. So we will leave this kind of pretty beautiful stuff, which can be explored on infinitum, We would start talking about the prime numbers as the building blocks of the integers, and on and on. A very beautiful subject. But for us, we will move on. And here we come back to our whole numbers and back to the prosaic division of the even numbers and the odd numbers. And again, we're still kind of just playing with numbers, but now my focus here, my intention is a bit more serious. I want to work towards a certain kind of proof method and prove something very, very important to us: the irrationality of radical 2, the square root of 2. That's what this whole little set of slides is about. So we have even and odd numbers, stuff that we know all about. But again, if you look at the whole numbers, 0, 1, 2, 3, here we are in this infinite world. If you simply double them, if you double every whole number, you will generate the even numbers. We call the whole numbers set W. We can call the even numbers the set capital E. And if we take 2W plus 1, that is, take every whole number, double it, and add 1, notice you will generate all the odd numbers, even starting with 0. 2 times 0 plus 1 is 1, and 2 times 1 plus 1 is 3, etc. Here again, we're looking at the world of the infinite. There seems to be an infinite number of even numbers, even though it's a subset of the whole numbers. It's only half of the whole numbers in one sense. The other half is down below in the odd numbers. But yet there are, in fact, an infinite number of even numbers and an infinite number of odd numbers. We can see that just with the dot, dot, dots, but there's even something more, more mathematical to say. You can see my hands. I think you'll all agree that I have the same number of fingers on my right hand as my left hand. We don't need to know about the number 5 to make that statement, because I've paired off every finger on one hand with the other. Whatever number it is, they in fact have the same number of fingers because of this one-to-one pairing. That's why I can say that there are as many even numbers as there are whole numbers, even as paradoxically as that sounds, because clearly they're paired off right there. 0 is paired off with 0, and 1 with 2, and 2 with 4, and 3 with 6. Clearly, there is an even number to pair off with every single whole number. The only reason why we can do this is because they go on to infinity. They never stop. Because we're working in the world of the infinite, we have this charming idea that the part can have as many elements as the whole. This is not true in the finite world, but yet it is true in this world, the world of the mind, and we see it here. Some theorems. The sum of 2 even numbers is even. Let me rephrase that because we do want to talk about the structure of proofs here, and sometimes rephrasing in a more of a mathematical way helps us see the structure of the theorem, structure of what the sentence is saying. So let me just rephrase that by saying if A and B are even, then A plus B is even. Clearly that is equivalent to the sum of 2 even numbers is even, but it gives us a more of a structure. If A and B are even numbers, by the way, these numbers here for these early theorems are all going to be, we'll assume I'm using the word number, but we're talking about integers. Okay, we're not talking about fractions and radical 2 and pi. We're in the domain of the whole numbers. So if A and B are even, then A plus B is even. We can prove that. If A and B are even, then there exist numbers m and n, some numbers, so that A is 2 times one of them and B is 2. If they're even numbers, then they're both 2 times something or other. We can see that from the top. Every even number is 2 times something or other. I don't care what m and n are. I just know that if A is even, A is equal to 2 times something. I'll call it m. B is also an even number. Well, it's 2 times something else. Call it n. So now when we look at the sum of A plus B is 2m plus 2n because A is 2m and B is 2n. And I can factor out the 2, the distributive law backwards, and which has that number 2 times m plus n does have the form of an even number. It's 2 times something. And that's what even numbers look like. So in fact, A plus B is an even number. Here's a couple of theorems I'd like you to try yourself. All of the exercises and homework problems and quotes that I would like you to try are written in blue. Okay, and the solutions that I will give you to those problems will also be written in blue. So it's kind of a convention that we can use to distinguish. So the sum of two odd numbers is even, and the sum of an even and an odd number is odd. Take a try at those, trying to use my proof of theorem 1 as a model. The first thing I would suggest is that you rewrite them as I have, using explicit numbers, calling them A and B, so we have something tangible to work with when we now know that they're even and odd, etc. Okay, we can see the general form. The general form of an even number is 2 times something. The general form from an odd number is 2 times a number plus 1 more. Every single odd number can be written as 2 times something plus 1 more, and you can use that as a general term for an odd number, just as I have for the evens. So give that a try. Okay, mathematical statements and their proofs. Let's prove another theorem. Theorem number 4, I'm calling the product of an even number and any number is even. So to convert that into something that really shows the structure of the theorem, I like to put it into the structure of if the premise is true, then the conclusion is true. The product of an even number and any number is even. Can I turn that into that kind of a structure? If P, then Q. P implies Q. Even symbolically, if you study symbolic logic, you can write it purely in a mathematical notation, P arrow Q. That's the meaning of if P is true, then Q is true. So let me rewrite theorem 4. If A is even and B is any number, then AB is even. Kind of really brings out the structure and gives us already something to work with. We now have 2 numbers, A, which is an even number, and B, which is any number. How can I prove that AB is even? Well, if A is even, start the same way, then there's some number n so that A is 2 times that number. It's an even number, it's 2 times something. So what is AB? AB is 2n times this number B. B is anything. Well, by the associative law, son of a gun, there's the associative law of all things. Instead of multiplying 2n and then multiplying by the B, we can go ahead, multiply the NB and then multiply. Yeah, it doesn't matter what order that you take the grouping. And so look at what AB is. AB is 2 times something. It's 2 times this number NB, which indeed has the form of an even number. This little symbol here, guys, that I'll be using, this means that the proof is ended. We're done. This is the more kind of a more modern notation for the Euclid's wonderful QED. So this become a kind of a standard thing that you'll see in math textbooks, saying that it's the end of the proof. Okay, we have a corollary to theorem 4, that the square of an even number is even. A corollary to a theorem is also a theorem, but its proof follows almost immediately from the previous theorem. So something to be a corollary of theorem 4 means if you look at theorem 4 tells you almost immediately that this thing is also true. So the square of an even number is even. Again, we write it in that structural form. For any number n, if n is even, then n squared is even. That's the equivalent kind of structured way of putting into if P, then Q. So if n is even, then n squared is even. That is my theorem. But if n is even, then by theorem 4, n squared is n, which is an even number, times something. Doesn't matter if it's the same thing. It's an even number times something. And we know from theorem 4 that any even number times anything is even. So even n times itself must be even. You see how it's a corollary, follows immediately from the fact that n times any number is even itself. Okay, the product of 2 odd numbers is odd. If A and B are odd, then AB is odd. Well, if if A and B are odd, then there exist numbers m and n. So A can be written as an odd number, 2 times something plus 1, and B can be written as an odd number, 2 times something else. By the way, A and B don't even have to be different numbers. Okay? The theorem doesn't say that. M and N could be in fact the same numbers. But the point is, no matter what the odd numbers are, 3 plus 3, I'm sorry, they were doing products. 3 times 3 is an odd number. It's 9. Okay, they can be the same number, but in general, okay, they're different numbers as we write them down. And so what is the product of AB? Well, it's 2m plus 1, the first odd number, times the second odd number. And here we again have another little piece of algebra here. We're not going to use our algorithm that most of us remember from long ago. Well, let's use very slowly the distributive law. Let's take this expression 2m plus 1. After all, it's only a number. Let's multiply 2m plus 1 through the bracket. Multiply 2m plus 1 times 2n, and then we'll multiply 2m plus 1 times 1. I'm simply using the distributive law, thinking of 2m plus 1 as what it really is. It's just a number, some odd number. Okay. I can simplify that a little bit. I can multiply now the 2n through the bracket the other way, using the distributive law going in the other direction, and I get 2 terms, 2n times the first term, 2n times the second term, 1, and of course 1 times 2n plus 1 is nothing more than 2n plus 1. We know that from our identity law. Well, I can simplify this 1 times further, right? 2m times 2n is 4mn, and 1 times 2n, okay? And certainly I can factor a 2 out from the first 2 terms, right? Using the distributive law backwards. The whole factoring game, very interesting, very important, very useful. And look what I have. I have a number in the form of an odd number. It's 2 times some mess plus 1. That's an odd number, because 2mn plus m, whatever that is, it is a number. And 2 times it plus 1 is in fact an odd number. Okay, let's discuss the converse and the contrapositive of a mathematical statement. This is the reason why I asked you to look at the structure of these statements, because now looking at the structured form of these statements is much easier for us to think about things like converses and contrapositives. So I have a new theorem for you, Theorem 6. This is the converse of that corollary. The Theorem 6 says, corollary, the Theorem 6 says for any number n, if n squared is even, then n is even. Remember corollary 4? For any number, if n is even, then n squared is even. The converse turns it around. The converse says, oh, if n squared is even, then n is even. The converse is a totally different statement, okay? Just because some statement is true doesn't mean that the converse is true, not at all. If I win the lottery, then I'm going to take a trip to Europe. Could be a true statement, okay? If I take a trip to Europe, does that necessarily mean I won the lottery? No, not necessarily, okay? If a four-sided figure, if a four-sided figure is a square, then all of its angles are right angles. If a four-sided figure has all of its angles as right angles, then it must be a square. No, could be a rectangle. Okay? So the converse of a statement is not necessarily true as the original statement. Sometimes they are. The triangle has 2 equal legs, and the base angles to those legs are equal. That's just as true as in the triangle. If the base angles of a triangle are equal, then the 2 corresponding legs are equal. The converse is true, but that's a theorem that has to be proved. You have to prove that in 2 separate directions, because one does not necessarily imply the other. So we'd like to prove Theorem 6, the converse of the corollary to Theorem 4, and we try the method we've been trying so far, called the direct method. We'll just assume the premise. We'll assume that n squared is even. Then we've got the old game that n squared is equal to 2 times something, 2 times some number k, and so n times n is equal to 2k, but then it's not really clear how to go here. Where does this lead? We're trying to get back to n. There's no direct way to do this. We would need to introduce more mathematics. We'd have to start talking about prime numbers and the structure of numbers to continue along this route, which we're not going to do. We don't have the theorems on prime numbers. So we need another way to prove Theorem 6, that if n squared is even, then n is even. I want to introduce another statement which is equivalent to if p then q. And that will lead me to a way of proving if p then q by proving its equivalent version. So a second method of proving a theorem in the form of if p then q, if some premise is true, then the conclusion is true. The statement if p then q is equivalent to the statement if the conclusion q is false, then the premise p is false. Okay, so if p then q is truly equivalent to if not q, then not p. And this is called the contrapositive of if p then q. And they are in fact equivalent. If it is snowing, then I won't go shopping. That's equivalent to if I go shopping, it must not be snowing. Because if it was snowing, then I wouldn't have gone shopping, right? If I'm assuming that that's first statement is true, then if I go shopping, then it can't be snowing because of the a more mathematical statement, if n is a prime number, then it only has two divisors. That's equivalent to, you could prove the same statement by saying that if n has more than two divisors, then it's not a prime number. We're going to use that with our Theorem 6. We're going to use what's called proving the contrapositive of a statement, and that's a method of indirect proof. There's a couple of ways of doing an indirect proof. Here's one of them, proving the contrapositive. So we have our statement. For any number, if n squared is even, then n is even. Proof indirect. Assume that n is not even. Assume that your conclusion is false. Let us see if we can get to the fact that the premise must be false. If n is not even, then it must be odd. But then by Theorem 5, we know that the square of any odd number is odd. And so therefore n squared is not even. And yes, the sentence in red in the beginning has led to the conclusion of the sentence in red at the end. And that is exactly, if not q, then not p. So here's a second method of proof. We have the direct method where you just start with p and run with it. Or you could start with not q and see if you can wind up with not p. And this is called proof by contrapositive. It's an example of an indirect proof. Okay, let's run through the other numbers of algebra. Because we have the beauty in the world of infinity, we can take the whole number line, the whole numbers from 0 on infinity, and just put a mirror up against it, just flip the whole thing over and have the negative integers going on to infinity in the other direction. And we can do this in Plato's world of ideas with no trouble at all. The mind has no trouble doing this forever. Not only do we have infinity reaching out to the right forever and ever, we now have infinity reaching out to the left. It's amazing what the mind can get used to. And here are our increasing numbers. Yes, -4 is less than -3, and -3 is less than, the numbers increase as we go, just as the numbers were increasing with the whole numbers. It stays that way. We don't change that. -100 is a very small number compared to -1 or 1. So we can add sign numbers. We have represented here a +4. We add a -2 going the other way, and we wind up with a +2. We can go ahead and add a -4 to a +2 and wind up with a -2. So we can generate the laws of adding sign numbers by using this kind of vector geometry. Make it very, very visceral. And sure enough, all the laws of sign numbers will follow this kind of a very simple geometry. This is the fundamentals of why the laws are what they are. But this is what we learned, right, in maybe 8th grade, at least in 9th grade. The rules for adding sign numbers. When the signs are the same, you add the two numbers and keep the sign. So a minus plus a minus is another minus, etc. When the signs are different, you subtract the numbers and you keep the sign of the larger. Okay. This, guys, is an algorithm. It's a rule. Okay. It does not explain what sign numbers are or why this rule works. Why the rule works is up above. It's because of this geometry of arrows. Okay, if we build in this geometry of arrows into representing our sign numbers, then these rules must be so. This is just an expression of the rules. This is a formula, a recipe to follow to add sign numbers that incorporate, that encode the arrow geometry that's above. This is an algorithm. It is not the fundamental principles of what the addition of sign numbers are. It's a wonderful recipe and it works every single time. This is a theme that we'll be talking about all throughout our course, the difference between understanding the mathematics and understanding the algorithms that we use very, very often. And algebra, as we know, is filled with these algorithms to help us manipulate our algebraic processes. The algorithms are not the mathematics. They are recipes which allow us to do the mathematics. And this is why, I've been harping here in my emails to you saying, you can't learn mathematics unless you do mathematics. Well, actually, that's certainly true, but it's not enough. You can go ahead and learn all the algorithms. You can be very good at learning algorithms and how to apply them accurately and get the right answers. You can do the mathematics from the outside by doing these algorithms, but if all you understand is following the algorithms and you're very good at that, you may not actually be understanding the mathematics. And maybe some of you may have it in somewhere in your mathematical career has experienced that in some way. Yeah, one way it shows up, I know the math very well, but I can't do the word problems. Yeah, because the algorithms that you have to use are more hidden inside the word problems. And some people are very good at reading the word problems, seeing the example word problems, and knowing how to apply the algorithms. And they even get beyond the word problems. For those of you who remember your calculus very, very vaguely, you remember the great algorithms to differentiate, to differentiate a function. Really very simple rules that came down to find the derivative of x cubed being 3x squared. A simple algorithm. But what's the derivative of x cubed? Now, that's an idea. That's a mathematical idea that 3x squared is not going to give you. That's just going to give you what the derivative is as an algorithm, as a second algebraic expression. It doesn't tell you. Okay, I don't want to beat a dead horse here. But the idea of learning the algorithms is not enough, guys. And here's your second chance, because you're a wonderful, courageous group to sign up for a class like this. Let's try to get beyond the algorithms. And here's just a very simple example, okay, where we have the arrow geometry on one side and the algorithm on the other. I'm sorry, Jenny, did you say something?
I said there's one question.
Yes.
Is this use of algorithms how math is taught in school today?
Thank you. That is my next point. You are right. Thank you so much for that question.
Michael.
So, what's that?
I just said it's from Michael.
Michael who? I guess we don't know.
Haslam.
Okay. Michael, thank you very much. This is one of the great things about teaching math, okay? And why many people hate math and never actually understand math. Because many of the teachers, many of the elementary school teachers, they know their algorithms to arithmetic very, very well, but they don't know the mathematics behind it. And all they wind up doing is teaching algorithms. And if you continue that in middle school and in high school, where the high school, certainly math teachers should know better, but it's easier to teach algorithms than to teach real math. And unfortunately, the tests are testing you on how well you can do you see, it's kind of like, and you wind up finishing and you can do very, very well. You can be an A student, know the algorithms very well and not really understand the math. And this is why math is, well, in the shape that it's in many, many ways. It just seems to be a big jumble of rules, which, you make the teacher happy by applying the right rule to the right situation. They mark it right. So there you go. We will come back to this theme again and again, because I want to try to emphasize we're looking here for understanding, but we need to understand the algorithms, because if we don't use the algorithms, then we'll be bogged down and we cannot make any progress. These algorithms are incredibly powerful, incredibly useful, and we need to use them. They are an essential component of mathematics, but they're not what underlies mathematics. Okay, let's move quickly to finish this. Multiplication and division, again, we have the rules. If the signs are the same, it's a positive. Plus times a plus, minus times a minus are both plus, and minus times a plus is a negative. Okay. We have no problem with multiplication of two positive numbers. That seems to make sense. 3 times 4 is just adding up 4 3 times. Well, you add positive numbers, you get positive numbers. 3 times a minus 4, that makes a lot of sense. You're adding minus 4 3 times, or you keep adding negative numbers, you get a negative number. This is the weird one, okay? Minus 3 times minus 4 is 12. Well, it's a rule. We'll just memorize the rule. No, there's a reason why it is. There's a reason for everything, okay? And if you're interested, you should find out what that reason is. Mathematics is not based upon rules. It's based upon, well, it's based upon those rules, like those axioms that we first saw, and proving things using those axioms. So here's a theorem. As opposed to 3 and 4, let's use 1 and 1, because if it's true for 1 and 1, it'll be true for everything. A minus 1 times a minus 1, I claim, is 1. Let's do our proof. 0 was certainly minus 1 times 0. 0 times anything is 0, even minus 1. Well, 0 can be written as 1 plus a minus 1. But we can use the distributive law and multiply that minus 1 outside through, and we get minus 1 times 1 and minus 1 times minus 1. So look at what 0 is. 0 is minus 1, because that's only 1 times minus 1. 1 times anything is what it is. So 0 is minus 1 plus this strange term of minus 1 times minus 1. But we know that only minus 1 plus 1 will give you 0. That's the only number that you can add to minus 1 to get 0. So that term in red must be the number 1. Okay, the fractions. The wonderful fractions. This is a dividing line between many, many students in mathematics. Some students never get this. I hope there's no one here who is in that situation. Everyone here has gotten over the great hurdle of elementary school and middle school of dealing with fractions. But what I do want to remind you is that fractions, of course, even the whole numbers can be written as fractions. 0 is 0 over 4. 1 is 4 over 4. What's interesting about the fractions is you take 1/3 and 2/3, and I can rewrite those as 2/6 and 4/6. Okay? And sure enough, I can easily find a fraction in the middle. A fraction between 2/6 and 4/6 is 3/6. I can take those two fractions, 2/6 and 3/6, turn those into 12ths. 2/6 is 4/12, 3/6 is 6/12, and I can easily find the number in the middle. We can do this all day, right? We know this. Okay? Between any two rational numbers, there's another rational number. And again, we're into the world of the infinite. If between any two rational numbers, no matter how close together, no matter what they are, I can find another fraction in between the two, how? Just by taking the average, for example. Then we again into the world of the infinite. There's an infinite number of numbers between any two numbers, no matter how close they are. We can only understand this in the mind, in the area of Plato's world of ideas. And the fractions are the basis of all of our measuring systems. Okay? All the numbers that are in this box that we're looking at in this computer, they're all rational numbers. Oh, I know you can write down radical 2. You can write down pi, okay, and you can do a manipulation. You can multiply them and divide them, and the computer will do them for you. But it doesn't know anything about radical 2. It doesn't know anything about pi. well, I'm sorry, I shouldn't say anything. It knows those numbers out to 6 decimal places, 8 decimal places, 16 decimal places, depending upon your operating system, depending upon what mathematical system you may be working in. But it doesn't know those irrational numbers. The computer only knows rational numbers. And in fact, think about it, the computer only knows a finite number of rational numbers. It's a finite machine, guys. Okay? It only knows a finite number of rational, there are an infinite number of rational numbers. It only knows a finite subset of them. But they worked it out so that most real mathematics can be done using that finite set that they give us. And of course, we know just as we have extended to infinity going on in both directions, we can take those rational numbers and continue on in both directions forever. Between 0 and 1, we can again go from 1 to 2 and 2 to 3, and all the fractions continue to follow. From 4/4 to 5/4 to 6/4 to 7/4. And the pizza pies still work. They work very well to understand, in some kind of conceptual way what fractions are doing. Parts of whole, 5/4 is simply 5 parts of the something which is, the unit of 4 parts. It works actually very, very well to conceptualize what fractions and rational numbers are about. Manipulating fractions, of course, adding fifths, 2/5 plus 7/5, we can say with the fifths. One of the great questions to ask in elementary school is, what is 2 apples plus 3 oranges? And the great profound answer, of course, as we know, is 5 pieces of fruit. The correct answer is also 2 apples plus 3 oranges. That is the correct answer. But if you want to add them together in some way, then 2 apples plus 3 oranges, you must find a common denominator. The only way to add things is by finding what's common about them. So here it's given to you in a silver platter. They're both given as fifths, so it's easy enough to add them. Okay. So in general, A over C plus B over C is nothing more than A plus B over C. Multiplication is even easier. You simply just multiply across. You don't need anything common. Multiply the 2 times the 7, the 5 times the 4. Nothing simpler. 14 over 20, reducing to lowest terms, being polite. The general rule for multiplying fractions, you multiply across. Multiply the numerators, multiply the denominators. But when we don't have a common denominator, what do we do? Okay. Well, we need to make a common denominator, and here's the mathematics behind it. I can multiply anything by 1, and 4 over 4 is 1, and 5 over 5 is 1. This will make that 2/5 into something of 20ths. That 5 over 5 will make those 4ths into something of 20ths. Then I can go ahead and add them. By using the laws of multiplication, 2 times 4 is 8 20ths, and 7 times 5 is 35ths. Now I've got everybody in 20ths. That's the mathematics behind why we can do this. That's the algorithm. We know the algorithm. You find the common denominator. Not, by the way, the least common denominator. We don't need to. There's a lot of time and energy has been spent with the obsession in elementary school and middle school of finding the least common. Any common denominator will do. What happens if you don't use the least? You'll just have to reduce the fraction to lowest terms when you finish. You'll get the right answer. Life is too short to obsess about the least common denominator. But it's easy enough to get the least common denominator here of 20. And now we have the algorithm that we know so well. It's a sing-song. We learned this in 4th grade or 5th grade, whatever. 5 into 20 goes 8. I'm sorry, 5 into 20 goes 4, and 4 times 2 is 8, and 4 times 2 is 5, and 5 times 7. Okay? And that is our algorithm. Okay? That's how we all add fractions. Okay? It's a wonderful and powerful and simple algorithm, and we will use it exactly the same way in algebra. But that's not what's going on when you're adding fractions. It's what's above is what's going on. That's why we're allowed to have that embodied in the algorithm. Okay, we're coming to the end here. The Pythagorean theorem. This was wonderfully shown in one of the videos I asked you to watch. You basically you express the area of a square of side a plus b in 2 different ways. on the one hand, a plus b squared is the middle square, c squared, plus the 4 rectangles. And each rectangle is height times width over 2. The height, width are a and b, so all the rectangles have the same area. So you can write that square as c squared plus 2ab. But rearranging the rectangles, putting them together, rearranging the triangles, putting them together as rectangles, then we now have them as, AB as the 2 rectangles. And we can write that square again equivalently in another way, a squared plus b squared. They're both the same size square. And notice when you cancel out the 2ab, you get the Pythagorean theorem. Again, if you haven't checked out that video about how many ways to prove the Pythagorean theorem, it's a cute video and has this proof and a couple more. It's very nicely animated to show this proof. So we come to what I wanted to show was the irrationality of the square root of 2. Square root of 2 is a perfectly reasonable length. We have a square of side 1 according to Pythagorean theorem. That diagonal as of length, its square at least is 1 squared plus 1 squared, which is 2. So the diagonals of length, the square root of 2. It's somewhere on the number line. I can just drop the line and there it is. It's a place on the number line, but yet it's claimed that you can't write it as a fraction. If you think about that, it's crazy. There are an infinite number of fractions. I mean, I can break up that line between 1 and 2 into halves, which I have. There's 1.5 there. You could break it up into thirds or fourths or hundredths or millions or a googolplex. You can divide that thing up into a mesh as fine as you can imagine. There's an infinite number of meshes that you can use, finer and finer, and none of those hash marks will hit that place. Are you kidding me? How can that be? This is one of the great, of course, discoveries of the Pythagoreans. So I like to prove that. And in order to prove that, we need another kind of proof. We need another kind of indirect proof, because called proof of reductio ad absurdum, or proof of reducing to the absurd. It's based upon the fundamental principle of the law of the excluded middle, that given any proposition, if it's truly a proposition, then it's either true or false. If it's true, then the false of it must be false, and if it's false, then its false must be true. Okay, they have to go back and forth. There's no middle ground. There can't be both. So the whole method of proving something indirectly by proof of contradiction is we prove that it must be true by showing that it can't be false. It's a fascinating way to do things. You prove that the sky is blue by showing that the fact that it's not true can't be false, that it cannot be false. I do that by assuming that it is false and coming up to something which I know is just simply not true. So I prove something is true by showing it can't be false, because I'll get something which clearly is absurd. I've used all good logic to get there. How did I get something which I know is false if I used good logic? I must have started with something which was false. So there's the structure of the proof, as we just said, and let's use it. I claim that radical 2 cannot be written as a fraction of one integer over the other. Proof is indirect by reductio ad absurdum. Suppose the statement is false. I'm going to come to something which I know is false, given these statements. If I assume the statement is false, what also must be true? Well, let's make the statement that radical 2 is equal to a over b. I can assume that they're reduced to lowest terms. Every fraction can be reduced to lowest terms. They don't go down to infinity, okay? The integers have to stop at some point getting to the lowest terms. If a fraction is reduced to lowest terms, then they can't both be even, because if they were both even, I could pull a 2 out of both of them and they wouldn't be reduced to lowest terms. So I know that there's a over b, among other things, they're not both even. One could be even, but they both can't be. Otherwise, they wouldn't be reduced to lowest terms. And now the algebra starts. Let's square both sides. Therefore, a squared over b squared is 2. Therefore, a squared is equal to 2b, a nice little, right, algebraic manipulation. A squared is even. By our theorem, which we took pains to prove, a is even. We now have A is even. We're on the road. So A is equal to 2 times something. Let's go back to our formula. A squared is equal to 2B squared. Therefore, 2B squared is equal to 2 times K squared, which is 4K squared. Let's divide both sides by 2. B squared is equal to, 2 times something. B squared is even. Same theorem, B is even. We've got A and B both even. Look at the 2 lines in red. The first line is then A and B are not both even. And now, therefore, A and B are both even. This can't be so, but I've used perfectly good logic. What I started with cannot be so. It can't be so that radical 2 can be written as a fraction. It's quite amazing. So this is the first assault on common sense, because you would think that any point on the number line could be filled in with a fraction, since there are an infinite number of them. They're in fact infinitely dense, as a mathematician would call them, because between any 2 fractions, there's an infinite number of other fractions between any 2, but yet none of them hit this number. And we know it is irrational. Another most famous irrational number would be pi. Here we have a circle of radius 1/2. The radius is 2 pi r, which makes it equal to pi. If I do one complete circle, roll it out one revolution, I'll get a perfectly good distance of pi. Perfectly simple to roll out the number pi. But yet there is no place on the number line that a fraction can qualify to be exactly that number pi. Decimal place value, something I just wanted to remind you of, one of the great advances, again, of the Indian mathematicians, using the powers of 10. Okay, take a look at that, even down to the negative. Okay, 1/10 can be written as 10 to the minus 1. These are conventions that turn out to be very, very useful. Even 10 to the 0 has a number, it's the number 1. So this is how we write our numbers in place value. The value of the number depends upon not only the digit, but also what place it has in the number itself. And we come to the end. So here is our world. This is our infinite mathematical world containing all the numbers, the positive numbers, the negative numbers, the fractions, the integers, the irrational numbers. They're all here. And 2 more definitions before we go. The opposite of a number, or the negative of a number, is the number so that when you add them together, you get 0. So -2 is the opposite of 2. 9/8 is the opposite of -9/8, etc. Notice that if y is the opposite of x, then x has got to be the opposite of y, because of the commutative law. The inverse, or the reciprocal of a number, is a number. Y is the inverse if their product is 1. Notice the use of the units. Therefore, 1/2 is the inverse of 2, -9/8 is the inverse of -8/9 is the inverse of -9/8, etc. Again, the same statement. Notice if y is the inverse of x, then x must be the inverse of y, because of the commutative law of multiplication. But 0, in fact, is the only number that has no inverse, right? Because 0 times anything will give you 0. It'll never give you 1. And so it can have no inverse. And there we are. We've gone through our numbers, guys. Thank you for hanging on with me for this. Jenny, do we have any questions? And open up the mic if anybody wants to throw one out. Any questions, Jen?
There are no more right now, but.
Okay. Other people have any, oops, what did I do? People have any questions they want to unmute themselves and ask? Okay, I think, well, I'll assume we're good, guys.
There's one.
Sorry,
Okay.
that was my question. That was my question, and I didn't write it correctly. On the previous slide, shouldn't it be minus 3.62? I didn't understand why it was 3.62 on the previous slide.
Previous slide, where are we?
Why does it 3.62 and not minus 3.62?
You're absolutely right. Thank you. Thank you
Oh.
very much. I will correct that. Good catch.
Okay.
Thank you so much. Very
you.
good. All right, so next week we will be solving equations and we'll see how fast we can go. Please, guys, take a careful look at the presentation I sent you on Tuesday. Take a look at these equations. I've given you a ton of examples. For you math majors, for you math teachers, obviously you don't have to do them all. Clearly, they'll be very easy for you. But there for the, there were 9 of you who gave the responses. And again, thank you again, who say that your, the 9th grade stuff is a little shaky. This is what this presentation is for. It's for you 9, really. And also for the others to prove to yourself that you really do have a good opinion of. But take a look at that and try to do some of these equations even before our class on Thursday. And let's see how fast we can go. And let's see if an extra class would be helpful to some of you. All right, guys, have a great week and look forward to next Thursday. Bye-bye.
Bye.